All right, so we're in section 6.3 about the adjoint of a linear operator. We showed last time that on a finite dimensional inner product space, there is a unique operator called the adjoint associated to any linear operator T. Just to remind you, it was that operator that has the property that the inner product between T of x and y is the same as the inner product between x and T star of y. And we showed that backwards also works. So the inner product between x and T of y is the inner product between T star of x and y. So it's that operator that allows you to move around between the two entries of the inner product. Again, it has to be finite dimensional in order for this T star to exist. And all the spaces that we'll work with will be finite dimensional inner product spaces. Okay, so the idea behind this was that we needed an operator to kind of mimic the notion of an adjoint of a matrix, which we defined before, right? It is a transpose conjugate of the original matrix. And this T star defined by this relation here basically turns out to be exactly what we need, in the sense that whenever beta is an orthonormal basis for V, and that is essential that it's orthonormal, in a basis that is not orthonormal, this relation here might not be true. So if beta is orthonormal, then T star has the property that the matrix of T star in the basis beta is the same as the adjoint of the matrix of T in the basis beta. And the proof is not complicated at all. So let's call A the matrix of T in the orthonormal basis beta, and B the matrix of T star in the orthonormal basis beta, which is, let's say, V1 through Vn. All right, then we've seen that on an inner product vector space, you can find the entries of the matrix by just computing the inner product. So Bij is just, so those are the entries of the matrix of T star. So it's given by the inner product between T star and Vj, of Vj and Vi. And Aij, because it represents the entries of the matrix of T, will be T of Vj, inner product with Vi. For any two I and j between 1 and n. So then Bij, we can move, so we're looking here. I'm going to, well, I can use this relation here, that T star from the first entry can be moved into the second. So this is Vj, inner product with T of Vi. I'm going to switch the two entries by taking the complex conjugate. So this is the complex conjugate of the inner product between T of Vi and Vj. But if you look at this, the inner product between T of Vi and Vj is in fact Aj, right? You flip the two indices, and you need to take the complex conjugate of Aj. But in terms of matrices, that is exactly that operation of taking the transpose and the conjugate at the same time. So this says exactly what we need, that B is the adjoint of the matrix A. Okay, so nothing too complicated to check that. And as a corollary, something similar works for matrices. In the sense that, remember the left multiplication operator, right? When you left multiply a vector by the matrix A. left multiplication by A star is the adjoint of the operator left multiplication by A. Right. And the reason for this would be if beta is an orthonormal basis for, well, for which space? If you have an n by n matrix A, left multiplication by A would act on Fn. Right, because you multiply by a vector, an n by 1 vector, and you get an n by 1 vector, so an n tuple in Fn. So if beta is an orthonormal basis for Fn, I don't even need to look too much for that, because in Fn we know that the standard basis, the E1, E2, En, is orthonormal. We checked that before, so it's just the standard basis. Standard order basis. We checked before that in the standard ordered basis, the matrix of left multiplication by A is just the matrix A. So A star is left multiplication by A in the basis beta star, which according to the theorem above is LA, is the adjoint of the operator LA. LA, all star. But A star, because of the same reason as here, will be the left multiplication by A star, the matrix of the left multiplication by A star. So here it is. You know, when you have two operators that coincide in a basis beta, that means they have the same coefficients. It means that they coincide on the basis, so they are equal. Okay, so I don't know if it's clear what I'm trying to say here. Probably not. So I have to let me rephrase that. If you have a basis beta and two operators T and U that have the same matrix in the basis beta. What does that mean? It means that the two matrices are equal entry-wise, right? But the ij entry of each matrix like that is just the inner product. Or actually not. No, even simpler than that. I don't need to look at the ij entry. I just look at each column. Because a column of that matrix associated to a linear transformation is just given by T, the column I is given by T of VI, written in that basis, right? So T of VI, which is the ith column of the matrix on the left, is the same as the ith column of the matrix on the right, and that is U of VI. Right, so T of VI equals U of VI for every VI in the basis. When two operators correspond on a basis, are identical on a basis, they will be identical everywhere. So that's exactly what I was trying to say here. L sub A star and L sub A everything star, the two matrices in the basis beta are equal, therefore the two operators must be equal, which I concluded over here. Then. All right. Back to the adjoint, very nice and natural properties here. The adjoint of a sum of two operators, T and U, is the sum of the adjoints. Let's prove them one by one. All those proofs will go directly to the definition, so they all follow pretty straightforward from that definition, which tells you that you can move a T to the other entry with T star. So we'll start with the inner product between X and T plus U adjoint of Y. I can move T plus U into the first entry. But T plus U is in fact T of X plus U of X. Inner product with Y. The inner product is linear in the first. Then t can be moved in the second with the adjoint. Same for u. Under addition, the inner product behaves nicely in the second as well. And then regroup the second as the sum of two operators. And here it is. And this holds for every x in V. And you know that whenever this happens with x first entry in both, then the second entry must be the same. So we're done with the first property, A. All right, so again here I'm using that thing, if xy equals xz for every x in the space, then y must be equal to z. That's a property that we proved at the beginning section about inner product spaces. And it's a pretty essential property, I would say. This one is very, very useful in a lot of proofs. All right, let's try the second one. It's going to be pretty similar to this. So I'll start with the inner product between x and the operator c times t. C is a scalar, star, adjoint of this, of y. Try to follow the same idea. So c times t is an operator that will now move into the first. So this equals the inner product between ct of x and y. But ct of x is just c times t of x. From the first, you can just pull out the scalar. So this is c times the inner product between t of x and y. Now move t back with a star in the second argument. And put c back into the second argument now. So it's going to go in there with a complex conjugate. And again, this holds for any x in V. Therefore, according to the same property as above, the adjoint of the operator c times t is c bar times the adjoint of t. Okay. See? Tu is not a product, is the composition of functions, composition of linear operators. So Tu, inner product between x and the adjoint of Tu applied to y. So first, move the entire composition between t and u into the first. So Tu of x, inner product with y. But then, since it's composition, this is t of u of x in the first argument. And now I'm going to start moving them back into the second one by one. So I'll start with t, right? Just leaving the inside of t on the left side. and the inside is u of x, and moving t with an adjoint into the second. And then do it again with u, right? Take u and move it into the second. You're left with x in the first. That again holds for every x. Therefore, t composed with u, adjoint is u star, t star. Okay. B. Okay, D says, again, something natural, double adjoint should give you back the original operator. And if it makes sense if you think about matrices, right? Because if you take a matrix, take the adjoint, you do it again, transpose, conjugate twice, they would cancel out. So let's see how it holds for operators. So this you have to start it in the right way, otherwise it's not going to look nice. Here's the starting point. You start it like this. Because now, if you want, right, to create the double adjoint into the first, so you take t star from the second, apply the adjoint to it, it moves into the second as a double adjoint. So the inner product between t star of x and y is that. However, if I go back up here when we said this, that the adjoint from the first can actually be moved into the second. As t. This is the same as the inner product between x and t of y. And this again holds for every x. Therefore, t and t star are equal for any t double star. Sorry. So t of y equals t double adjoint of y for any y, therefore t and t double adjoint are equal. And finally, E. The adjoint of the identity operator is itself. So let's start with x adjoint of the identity applied to y. Move the identity into the first. So this is the identity applied to x, inner product with y, but the identity is that operator that leaves everything unchanged, right? So identity of x is just x. And this holds again for every x. Hence, the adjoint of the identity applied to any vector y gives you back that vector y. So the adjoint of the identity is the identity operator, because it doesn't change anything. All right, so this is the end of 6.3. We'll move on. This is supposed to be the beginning of 6.4. It's called normal. And self-adjoint operators. So those will be special classes of operators, really important in general in operator theory because they have really, really nice properties. We're going to look at those properties in connection to the diagonalizability from chapter 5, I think it was, right? And we're going to see how being normal or self-adjoint on an inner product space actually turns out to be equivalent to being diagonalizable on a vector space, which before, remember, we didn't have this extra structure of inner product space, right? We had that theorem about when an operator was diagonalizable on a vector space. The characteristic polynomial had to split, and then each eigenvalue should have a multiplicity equal to the dimension of the corresponding eigenspace, right? So now there will be nothing about those eigenspaces. Normality and self-adjointness, those two properties will kind of replace those ideas on inner product spaces. So to get there, we're going to need two technical results. One of them is this lemma, which we'll see a proof of. The other one is this Schur's theorem, which as a technical result is pretty important. The proof, though, is quite long and by induction, and I'm going to skip that. So if you're interested, you can look back into the book for Schur's theorem. But let's look into this first. So the first lemma here says that if you're dealing with a finite dimensional inner product space, and remember, I need that in order for the adjoint of T to exist, in order to make sure that makes sense. What this one says that whenever T has an eigenvector, T star must have one as well. It's not saying that it's the same one, and most of the times it will not be the same eigenvector. However, we're going to see that there is a connection between the corresponding eigenvalues of T and T star. So if T has an eigenvector, let's say V is that eigenvector. Let V be an eigenvector of T. With a corresponding eigenvalue lambda. Just to remind you, that means T of V equals lambda times V, which is a thing that we can also write like this. Replace V by identity of V. And in the end, V turns out to be a zero of the operator T minus lambda identity, right? If you look at it in this way. Okay, so here's how we're going to get to T star. To get to T star, we need to look at a certain inner product, and here is the inner product that we'll look at. Is the inner product between this T minus lambda identity of V, which we know it's zero, right? Inner product with X. X is an arbitrary vector in V. This will end up being zero. But now that it looks like this, we can use the properties of the adjoint. So we're going to take this entire operator here and take its adjoint and move it into the second entry. So I need the adjoint of T minus lambda identity applied to X. All right, but with the properties of the adjoint, we know, just the previous theorem that we proved, that the adjoint of a sum, right, is the sum of the adjoints, and whenever you have a scalar multiple, that turns into the complex conjugate. So we get V inner product with T star minus lambda bar identity adjoint, that's just identity, all applied to X. Okay, and here is the idea now, or the type of argument that they will use now. So 0, V was the eigenvector, right, of T. Well, it turns out that V is orthogonal. So, and this happens for every x, right? Now, since this happens for every x, what I can get into the second entry here is the entire range of the operator t star minus lambda identity, right? I get anything in the image or in the range. And because this eigenvector, which by the way, remember that eigenvectors cannot be zero, right? So this eigenvector V is orthogonal onto the range of the operator, I can conclude that the range is not the entire space. Does it make sense? Why? So basically what I want is that this operator is not onto. That's what I'm after here. But why does this hold? Well, if the range would be the entire space V, would there be a vector in V that is orthogonal onto everything in V? Because the range, right, could mean any vector in V. If my vector, the eigenvector V, is orthogonal onto anything in the range, there is no way the range would be the entire space because the zero vector is the only thing orthogonal onto. So what I'm going to just write it like this. Right, we checked before that the orthogonal complement of V is just the zero vector. Pretty much what this identity says here is that this vector, little v, is in the orthogonal complement of the range. Right, it's perpendicular to anything in the range, and that's why the range cannot be V. Okay. All right, so I said that's what I'm after. So what if it's not onto? Well, T star minus lambda bar identity is an operator from V into itself, finite dimensional inner product space, let's say dimension n. But anyways, it's the same dimension in the domain and the codomain. And remember that when this is the case, when the domain and the codomain have the same dimension, onto and one-to-one are equivalent, right? They just... So because it's not onto, it's not one-to-one. All right. So there exists a vector v1 in the null space of this operator, non-zero. But that means T star minus lambda bar identity of v1 is 0. So T star of v1 minus lambda bar v1 is 0. So T star of v1 is lambda bar v1. Which is exactly what I'm after, because this identity here tells me that v1 is an eigenvector of T star. Right? That's what it means to be an eigenvector. It's an eigenvector, though, corresponding to eigenvalue lambda bar. So complex conjugate of the original lambda. Okay, so let's put all this in perspective here. So we started with an eigenvector of t with corresponding eigenvalue lambda. We ended up with an eigenvector of T star, V1. It could be a different one. I have no control over V1. That's how we construct it. It's just an existence kind of thing. However, we know for sure that the lambda from T turned into lambda bar, right, for T star. So the eigenvalues are just complex conjugates of the eigenvalues of T. Okay. So now, what does Schur say? So we have a linear operator on a finite dimensional inner product space such that the characteristic polynomial of T splits. Then there exists an orthonormal basis beta for V in which the matrix of T is upper triangular. So now this takes us in the direction of diagonalizability, right? Diagonalizability meant the existence of a basis in which the matrix would be diagonal, right? However, the only assumption that they have here is that the characteristic polynomial of T splits, right? Which is way less than we had before. And under that assumption, it turns out that, so that assumption is enough to have an upper triangular matrix. It's not diagonal yet, but still it's pretty nice, right? So this will be kind of the, a building theoretical result for us. We'll use this a lot today. Okay. So going in this direction of you know, diagonalizability and the matrix, the associated matrix of T being diagonal, let's see what it would mean if a basis existed such that the matrix of T will be diagonal. What would it mean for us and, you know, for the operator T on an inner product space and for the adjoint? So if beta is an orthonormal basis for V, such that the matrix of T in the basis beta is a diagonal matrix, which pretty much means that T would be diagonalizable. All right, so this matrix that is diagonal. If I take the adjoint of a diagonal matrix, what happens? Take the transpose, it remains diagonal, right? But just take the complex conjugates on the diagonal, but still is a diagonal matrix. Right, so this one is diagonal. But we've seen that we can move the adjoint in with this kind of matrix. So T star in the basis beta is also diagonal. All right, but the nice thing about, one of the nice things about diagonal matrices is that they commute, correct? So the product between two diagonal matrices is the same either way, because all you have to do is to multiply the diagonal entries. So you have, you know, number multiplication, which is commutative. Well, like this. Those two are diagonal, so those two commute. The matrix of T and the matrix of T star being diagonal, they commute. The product of two corresponding matrices is just the matrix of the composition. So T star composition equals the composition between T star and T as matrices, but remember that we said that this is enough because then every column is equal, so the two operators T star and T star T would agree on a basis. So T must have this kind of property if such a base is beta, orthonormal. Why do I need it to be orthonormal? Because I want to be able to do this. Remember that I can put the adjoint in, move it around only if I'm dealing with an orthonormal basis. So if an orthonormal basis existed such that the matrix of T in that basis is diagonal, then this must be true, right? We're going to call an operator that has this property, we're going to call it a normal operator. Is it here? I think it's on the next page. Yeah. So, an operator on an inner product space is called normal, provided that T star equals T star T. And similarly for a matrix, A star A should equal A star. So according to the remark that we made before, in the matrix of T, in some basis beta that is orthonormal, if the matrix of B in such a basis is diagonal, then T must be normal. And we're going to actually look for an if and only type of condition here. So between that, because after all, this means diagonalizability for T. And it turns out that it's going to be an if and only if condition as long as the space is a complex vector space V. So we'll get there. Basic examples of normal operators. Identity. Why is the identity normal? I star equals I, so I star is the same as I star I. A matrix A that is let's say symmetric, real symmetric. What happens with the adjoint when it's real symmetric? What does symmetric mean? Symmetric means equals its transpose, right? So being real, complex conjugates will not do anything. So I'm pretty much saying again that A equals A star. So then, of course, it's normal. So what I'm listing here so far are operators or matrices that have a stronger property than being normal. Those types of matrices and operators will be called self-adjoint. We'll talk about them later on. So those would be stronger than normal, but that will imply normal anyways. They don't have to be self-adjoint in order for this to work. For example, real and skew symmetric. Skew symmetric meant that the transpose is negative, the original matrix. Okay, so what is A star? Well, it's real, right? So the star doesn't do anything. It's negative A. So A star, and A star A, they will both be negative A squared. So they are equal to each other. Right, it's not that stronger property anymore. It's not self-adjoint anymore, but it's still normal. Okay. So again, I'm aiming to show that being normal is equivalent to being diagonalizable on a complex inner product space. I'm going to need some properties first. Those are the properties of normal operators. They're going to be really important for examples in this section. So those 4 properties are really nice. So T is assumed to be normal. Oops. So T is assumed to be normal. Then we have the following properties. T and T star turn out to have the same norm for every vector x. Let's look into that. So if I look at the norm, I would rather try to compute a square, right? Because it's the inner product between T of x and itself. Okay. So now you can move one of these T into the other entries. Let's say we move the first T into the second. And this is where normality comes in, because being normal means that T star T is the same as T star. It is T star of x, which is in fact T of T star of x. So then take this T from the second and move it into the first with the adjoint. So we end up with the inner product between T star of x and itself, and this is nothing more than the norm of T star of x squared. In conclusion, the norm of T of x equals the norm of T star of x for every x. Okay. B by itself is not essential, so I would say A, C, and D are the main properties here. However, B is necessary for proving C. So here is what B says. T minus C identity is normal. This is just a straightforward computation. So to check that this operator T minus C identity is normal, all we have to do is to check that this composition gives you the same result. And we know what the adjoint of T minus C identity is. It's T star minus C bar identity. Okay, let's just apply to some x. So if and only if this holds, and then you can just start distributing things around. So T minus C identity of x is T of x minus Cx and so on. And this should equal T minus C identity of T star of x minus C bar x for every x. And then you apply T star to that. And then minus C bar applied to that. So C bar T of X plus C bar C, C bar Cx. T of T star of X minus C bar X minus CT star plus CC bar X. So now I just distribute everything. T and T star are both linear. So that's T star T of X minus T star of Cx minus C bar T of X. This term I'll just ignore because it's the same on both sides, right? I'll just cancel it out. So if and only if this equals T star of X minus T of C bar X minus CT star of X. And now T is normal, so those two things are equal, right? T star of Cx, T star is linear, so you can pull the C from inside out. So it equals C T star of X. And T is linear, so T of C bar of X is C bar T of X. So it holds. So just straightforward computation, I would say, for part B. Because T is normal, then T minus scalar times identity will always be normal. So let's go to part C. So let me remind you what we proved at the very beginning, that lemma. It was saying that if T has an eigenvector, then T adjoint has an eigenvector. We said that it doesn't have to be the same eigenvector, but the eigenvalues have that property that they turn lambda into lambda bar. Now, if T was normal, which it is here, an eigenvector x of T is also an eigenvector of T star. Okay, so more than that lemma holds. So they have the same eigenvectors, T and T star. Lambda and lambda bar, right? The eigenvalues are still related through complex conjugates, but the eigenvectors turned out to be the same now. Let's see why that's the case. So x was the eigenvector corresponding to lambda. So T minus lambda identity of x is 0. If you move everything to one side. But according to part B, T minus lambda identity, this was part B here, T minus lambda identity is a normal operator, right? So I'm going to apply part A to the operator T minus lambda identity. So the norm of T minus lambda identity of x is the norm of T minus lambda identity adjoint of x, which is the norm of T star minus lambda bar identity. All right, but T minus lambda identity of x was 0, right? Because x was an eigenvector corresponding to lambda. So the norm on the left is 0. Therefore, the norm on the right, this one, is also 0. So when is the norm of a vector equal to 0? Unless the vector is 0 itself, right? That's the only vector with 0 norm. T star minus lambda bar identity of x is 0. But that means exactly that T star of x minus lambda bar x is 0. So T star of x equals lambda bar x. X was non-zero, so x is an eigenvector of T star corresponding to eigenvalue lambda bar. All right, so the fact that T was normal, which was essential in this identity here, right? Otherwise, I couldn't have written this thing here, right? So that allowed us to come up with this thing that the eigenvectors have to be the same. In general, they don't have to, but for normal operators, they do. Part B. So now you have two distinct eigenvalues, two different eigenvalues, and they have corresponding eigenvectors, x1 and x2. So the eigenvectors corresponding to different eigenvalues must be orthogonal in the sense of inner product, right? So the inner product between x1 and x2 must be 0. Let's look at that. So let lambda 1 and lambda 2 be distinct eigenvalues of T with corresponding eigenvectors x1 and x2 respectively. So T of x1 is lambda 1 x1. T of x2 is lambda 2 x2. So I want to show that the inner product between x1 and x2 is 0. What we'll show is that lambda 1 times the inner product between x1 and x2 equals lambda 2 times the inner product between x1 and x2. So that's what we'll show next. But this is enough. Why? Because if you move everything to one side, is lambda 1 minus lambda 2 times that inner product, and we assume that lambda 1 and lambda 2 are not equal to each other. So this difference is not 0. Therefore, it must be the case that the two vectors are orthogonal to each other. All right, so let's start with lambda 1 times the inner product between x1 and x2. I'm going to put lambda 1 into the first component, because lambda 1 x1 is in fact T of x1. So this is the inner product between T of x1 and x2. I'll move T into the second. So this is the inner product between x1 and T star of x2. Now x2 was an eigenvector of T. Because T is normal, it is also an eigenvector of T star, right? With corresponding eigenvalue lambda 2 conjugate. So this is now x1 inner product with lambda 2 conjugate times x2. Lambda 2 conjugate goes out from the second entry as a double conjugate, so back to lambda 2. And that's what we needed. So again, this identity here is because x2, according to part C, is an eigenvector of T star with corresponding eigenvalue lambda 2 bar. To complex conjugate. Okay. Questions? All right. Let's see. Let's stop for a minute with this theoretical results and look at an example. An example that is based on these properties, so it's going to be it's not going to be a computational example, so it's going to be more theoretical as well. So let T, this is number 9 on page 376, or part of it at least. So let T be normal, be a normal operator on a finite dimensional inner product space V. Show that the null space of T and the null space of the adjoint are one and the same. Now this will be a very fast consequence of one of those properties, and that is property 1 there, property A. In the sense that if, let's say, X is in the null space of T, then of course that means T of X is 0, right? But according to property A, because T is normal, T and T star have the same norm for every vector, right? X. So the norm of T of X, which is of course 0, is the norm of T star of X. But again, T star of X is a vector of 0 norm. That's only possible when T star of X is 0. So X is in the null space of T star. And that could very well go backwards, right? With an if and only if kind of thing. If X is in the null space of T star, then T star of X is 0. Then the identity still holds, so they are both 0. So T of X is 0. So X is in the null space. So it all goes with if and only if here. Let's try. This is 2C. I don't know which page. Is the following operator normal? A plus IB, comma, A plus 2B. So what can you use in order to show that an operator is normal? What properties can you use? Well, if you look at the theorem here, it is not an if and only if kind of condition, right? So it cannot be used to show normality. It can only be used to show that something is not normal, if you want, right? So if you can find a vector x for which A fails, then you conclude that is not normal, right? Or if you find something that, I don't know, doesn't agree with property C or D, again, is not normal. But I wouldn't really go in that direction unless, you know, I just have some kind of revelation and I notice one certain vector that messes up one of those properties. So basically, to show that an operator is normal, you have one option. You just go to the definition. Okay. So all you can do here is to check whether T star equals T star T. Okay, but in order to check that, I need to know what T star is, right? So you need to find T star first. And we need to find it in general. Remember, we've seen some examples last time of computing the value of the adjoint at certain points. So now we want to find the formula for T star, okay, based on the formula for T. So let's work on that. So we start from the inner product. Between T of A, B, we're in C square, C2, so A and B are both complex numbers, and another pair, CD, in C2. This is the same as the inner product between AB and T star of CD. Right, so let's work with the thing on the left here, because we have control over that only. So T of AB is 2A plus IB and A plus 2B, inner product with CD. Nothing is specified about what inner product to take on C2, and that when that's the case, you just take the standard inner product, so that's the sum of xi, yi conjugate. So that is 2a plus ib times c bar plus a plus 2b times b bar. And I'm going to regroup them in terms of a and b. I'm going to do one more thing. Now, why do I do this? So I wrote it as A times the complex conjugate of something plus B times the complex conjugate of something, because I want to relate it to the right-hand side. The right-hand side is the inner product between the pair AB and whatever T star of CD is, which is another pair of two elements, X and Y, right? But when you take the inner product between the pair AB and the pair XY, you get AX star plus B Y star. Here it is, A X star plus BY star. So, and this should hold for any A and B and C and D. So T star of CD is D plus 2C, 2D minus IC. Right, those are the X and Y that we need to put in there. For any two CM. All right, so we got the adjoint. We need to check whether T is normal. So let's look at T star of something. Let's do maybe compared to T star T of AB. It should be equal or not for any two A and B. All right, so let's take the left side. This is T of T star of AB. T star of AB is 2A plus B, 2B minus IA. Right, I'm just replacing C and D in that formula by A and B in the formula for T star here. All right, and what is T of this? What was T doing? T is twice the first entry plus I times the second entry, comma, first entry plus twice the second entry. That was the formula for T all the way up in the corner. And that is 4A minus I squared A, so plus A, that's 5A, plus 2B plus 2IB. And 5B plus 2 minus 2IA. That would be the left side. And then we do the right side. So that's T star of 2A plus 2A plus IB, comma, A plus 2B. And T star does twice the first entry plus the second, and twice the second entry minus I times the first. So we end up with 5A plus 2I plus 2B. And 2 minus 2IA plus 5B, which is identical to the left-hand side, therefore T is normal. Okay. Let's look into this. So this is finally the last and the property that we were going after about normal operators. It turns out that T is normal if and only if. What is all this saying? There exists an orthonormal basis for V consisting of eigenvectors of T. So basically says that T is diagonalizable. There is almost no assumption. Other than this. So the vector space, it's a vector space over a field F, which in general for us it meant real or complex. This one is by assumption complex. And the difference between real and complex spaces comes in the fact that every polynomial splits over complex numbers. So that's why the assumption exists here. All right, so it is an if and only if kind of proof. I'll start with this one, because we've seen it before, actually. From right to left. So I'm assuming first that T is diagonalizable, so there exists a basis, an orthonormal basis of eigenvectors. So the matrix of T in the basis beta is diagonal. Is that argument that we've seen before? So the adjoint of a diagonal matrix is diagonal. But the adjoint of this matrix is the same as the matrix of the adjoint of T. So the matrix of the adjoint of T is a diagonal matrix. And two diagonal matrices commute. Right, so this is that remark, let's say, from the beginning that started everything. So they commute. So the matrix of T, the matrices of T star and T star T are identical in some orthonormal basis beta, which implies that the two operators are equal. T is normal. Okay. So this is an argument that we've seen before. So why is it an if and only if condition? Backwards. Assume that T is normal. And that V is complex. That's part of the assumptions here. And I'm going to go all the way back to, not to page 1, but to Schur's lemma, which says that if you're dealing with a linear operator for which the characteristic polynomial splits, of course it does, because the space is complex, anything splits over the complex numbers, then there exists an orthonormal basis beta for which the matrix is upper triangular. What does upper triangular mean? A11, 0, 0, 0, 0, A12, A22, 0, 0, 0, 0, and so on. Let's say beta is V1 to Vn. All right, so what is T of V1 if that's the matrix? The coefficients of T of V1 are given by the first column, right? A11 V1, but doesn't that mean that V1 is an eigenvector? Corresponding to eigenvalue A11. All right, but for V2 is not that nice because T of V2 is A12 V1 plus A22 V2, right? So it's not automatically an eigenvector. However, A12, to find an exact, precise entry in the matrix, all you have to do is an inner product. To find A12, you have to do the inner product between T of V2 and V1, right? All right. But this is the same as the inner product between V2 and T star of V1. All right, but T was normal, right? And V1 is an eigenvector of T. We've seen that this means that V1 is an eigenvector of T star, right? Corresponding to the eigenvalue complex conjugate of the original one, which was A11. All right, so we get A11 times the inner product between V2 and V1. And the basis was orthonormal, so in particular orthogonal. So, right, Schur said that the matrix is upper triangular. However, under the additional assumption that T is normal, we can figure out that this entry there is actually 0. So this is in fact A22 V2. So V2 is an eigenvector. And we'll keep going with the same idea until we fill out the entire matrix and it turns into a diagonal matrix by doing this. And that's exactly what we wanted, right? We wanted to show that there exists an orthonormal basis of V consisting of eigenvectors of T. The eigenvectors will be V1 through Vn, and those entries on the diagonal will be the eigenvalues. Okay, so I'll stop here. Sorry for taking 2 minutes extra time. So I'll see you on Wednesday. The announcement is on Canvas. We'll meet from 3:15 to 4:15 in this building, room 2218, I think. 2 rooms down the hallway. It's written in Canvas, exactly. I think it was 2218. And then we'll continue again, so you'll have 15 minutes and we'll continue with the rest. It's going to be a long day.
We're going to switch rooms after?
We'll switch rooms, yeah. This one is apparently taken before us, so.